My name is Brendan-Gregg. I work at Oracle as a principal software engineer. Apologies. Jim wrote the slide deck, much of the slide deck, and has listed me as a senior software engineer. I believe my title is principal. Jim Marrow sends his apologies. He can't be here at Oracle OpenWorld this week, so I'll be delivering the presentation. I've worked with Jim closely over the past year on DTrace, and so we do think alike. I'm quite familiar with what he was thinking, so I should be able to handle this. Just as a short introduction of myself, I work on the Fishworks software team at Oracle, and we deliver an appliance product. Since appliances are so popular these days, ours at the moment is a storage appliance, the 7000 series, and that uses Solaris under the hood, a version of Solaris that we're using, which has DTrace. And we've developed various ways to bring DTrace to the end user and provide virtualization for looking at storage protocol traffic. I also work on DTrace a lot, so I'm involved in the DTrace community and recently wrote a DTrace book with Jim Marrow, which has been handed to the publisher and will be released by the end of the year. But I've been using DTrace since it was before Solaris 10 was released. I was one of the early adopters. It's a very cool technology. I'm very glad to have been involved with DTrace. So here we're talking about using DTrace in particular for application analysis. It's an interesting topic because DTrace sometimes can get a rap as something that's for kernel engineers to look at the kernel, and it does do that very well. But DTrace is also very good at analyzing applications for a variety of reasons, as we'll go through. To start with, how many people have used DTrace before in the room? Cool. Basically, everyone's used DTrace. So what is DTrace? An observability and analysis tool, instruments all software, using thousands of probes, each providing data and a D language to process it. I think that's a very neat way to describe what it is. This is similar to the tool beef patty special sauce, lettuce, cheese, pickles, onion. And it does cover the important points. We've got user SP and DTrace plus kernel stuff is a main component of DTrace. Kernel and user-land applications. We've got dynamic or static instrumentation points. DTrace is not just about the dynamic stuff, as we'll see. Each providing data and the D language. Where is it? Oracle Solaris 10 onwards. Oracle Solaris Express, Mac OS X, 10.5, 10.6. I'm here on a MacBook at the moment, and DTrace is running on it. FreeBSD, John Birrell did the port, so we had that since 7.1, which you have to enable to use. It's not yet in Linux, but I've included a URL. There is a project to develop that, and that looks particularly interesting. What is DTrace for? Troubleshooting performance problems, which it's particularly good at. Profiling applications in the kernel, since it can see all software, and taking latency measurements. In the world of performance is about latency more than anything else. So, and I do a lot of performance analysis as part of my day job. With performance, you can often start off on the wrong foot if you're using system tools that are looking at physical components like disks and CPUs, where in many application environments, the CPUs may be busy, but the application's working fine. The disks can be busy, but the application's working fine. What matters is the application transaction latency. And either the application gives that to you as statistics you can enable, or you want some other way you can measure that. If you're the developer, you can add those statistics. DTrace has the advantage in that you can take them from arbitrary points or custom points in production without modifying the code. So it's particularly good for latency measurements, which particularly matter for application analysis, because that's the performance that customers are experiencing. Troubleshooting software bugs. So DTrace is also good for proving what a problem is and what it is not, and also measuring and quantifying the magnitude of the problem. So I don't know how many of you are software developers. With software, there's often a lot of bugs. There's also often a lot of performance suboptimalities that are well known. especially when you go to larger and complicated systems. Finding performance problems no longer becomes the challenge. For most applications that I look at, I can find performance problems everywhere. The difficulty is finding the ones that matter. So quite often I will be looking at what appears to be a performance problem that needs engineering effort to go and fix. And when I measure the magnitude of that, it's costing less than 1% of overall performance. So that's really important before you engage the engineers or developers to go and modify the code, being able to prove that it's worthwhile. And DTrace is excellent at doing that. And for analyzing software bugs, so with any sort of software bugs, especially if you have, say, functions returning errors, DTrace can trace those functions as they operate live. You can examine the error codes, you can examine the arguments, you can look at the software flow. So DTrace can be used especially if you have software running in a variety of production environments and you'd like the ability to tell a customer, I'm not sure if you're hitting this software bug, but please run this DTrace script and let us know the output. And you can customize the DTrace script for identification. Detailed observability, so hardware resources, CPU, disk I/O, and network I/O, and to examine them in the context of the application. So rather than just noticing that disks are busy, finding out if that actually matters, because often it doesn't. Often disks are doing asynchronous operations, especially when you're, say, flushing pages from a in-memory cache, normal part of write flushing. And customers can be staring at the disks that are maxed out, but it's not actually an application problem. There's no transaction waiting on that at that point in time. There may be reads behind the queue of writes, and again, DTrace can dig into that. But that comes back to proving that, or measuring the magnitude of the problem, proving that it actually has an effect. And I do that quite a lot. Detailed observability of unmodified application software, and you can see the entire software stack. This is something we've been saying for a while, and you may have seen these. I wrote this up, this particular diagram, many years ago. How did you analyze these in the past? Dynamic languages, user executables, libraries, system calls, kernel, and hardware. It typically required a variety of tools. So dynamic languages, you may have a developer environment that lets you look at function flow. One of the drawbacks there is you need to be running the developer environment. Maybe that's not in production. And maybe that has an overhead that changes the nature of the problem. User executables, so compile code, debuggers, things like truss or strace, also finding out what's going on in user/proc. For libraries, again, maybe there's a developer environment you can run to look at how it's using compiled C libraries, or maybe you're going to use some of the other system tools. System calls are typically easy to appoint using truss or strace. The kernel is an entirely different beast to analyze function flow into there, and what the kernel software is doing is a different suite of tools. And for hardware, another different suite of tools. Usually we infer what's going on from counters that originate in device drivers. The point of this diagram is that in order to examine the entire software stack, we need to spend a good chunk of our lives learning a vast and complicated toolset. I previously wrote a book with Jim Marrow and Richard McDougall on this, Last Performance and Tools. For a lot of people, they don't have the time really to get expertise in all the different layers and all the different tool sets, especially if you're dealing with multiple operating systems, especially if it's not really your main job. An advantage of DTrace is we can see all of the layers from one tool. So you do learn one tool, and you can associate the layers together. DTrace can't see hardware. DTrace instruments software as it's running, so it can't go and read voltages off a physical hardware device. It can, its visibility of hardware is as far as the device driver starts to send messages on the bus or I/O to the actual device. Also, if there's device driver for the bus itself, you can detrace it there as well. So we get to the boundaries of the CPU, and you can infer what the hardware is doing. Yes, to some extent. Since I've had those diagrams for a long, long time, it's better to actually see this demonstrated, and my publisher will be happy if I do a short plug for the book. Jim and I recently collaborated on a DTrace book, and one thing I particularly wanted to do was to show detracing every layer of the software stack. And I previously wrote a toolkit called the DTrace Toolkit. Has anyone used that? Okay, so a lot of people use that. There's a whole bunch of my scripts are in Mac OS X. The DTrace Toolkit was great. I did demonstrate a lot of different topics, but there were some areas that were difficult that I hadn't really done a lot with, and that's something that we've done with the DTrace book. It took almost a year. I came up with a list of ideal topics, and Jim and I forced ourselves to go through them and document them, but it is a much more complete reference than the DTrace Toolkit currently is, which means the DTrace Toolkit now needs to be updated because I've gone and finished detracing a whole bunch of new areas. And those topics include things like CPU, memory, disk, networks, SCSI, SATA, IDE, SAS, VFS, UFS. And it's not just Solaris, I also do a lot of these scripts on Mac OS X and FreeBSD, which was interesting. But out of the 230 scripts in there, it's over 900 pages. The publisher will probably shrink it a little bit and format it. Out of the 230 scripts that are in there, I think about 160 of them are new. So a lot of new scripts. And to give you since I think most hands went up when I mentioned the DTrace Toolkit, to give you an idea of that, so this might be a directory that's familiar to you. The net directory of the DTrace Toolkit, I had some scripts in there, say TCP Snoop for looking at TCP, I/O by process, variations on a theme, UDP stat, TCP stat, and ICMP stat, which is the MIB stuff from SNMP. And there's just one script, connections, which looks at the socket layer, FBT tracing the kernel. For something like TCP, the entire TCP/IP stack, that's actually pretty thin coverage, as it turned out when I sat down to do this properly. And how that now looks in the DTrace book. So this whole section here, the socket scripts, and I've got tracing client socket connections showing process and host, server socket accepts showing process and host, socket connection duration from connect to close, socket I/O by process and type, sorted by process, tracing the connection and first byte latency at the socket layer, looking at the busiest sockets, socket top, and also looking at socket errors. So these sound like some pretty fundamental high-level tools, and I just hadn't done it before. I hadn't sat down and figured out how to do this. And this is a little bit embarrassing because the provider that I use to do all of these is Syscall. Since sockets is a fairly generic and standard interface, you can actually write all of this from the Syscall layer alone. So that's one gap that I only realized I really had in the DTrace Toolkit until I sat down to look at every layer. And of course, there's the IP scripts and TCP scripts and ICMP scripts and Ethernet scripts, because we were interested in looking at this thing. So not just an academic diagram, but actually showing how to detrace all of those layers and giving you examples you can start to use and tweak for all of those layers. And that's a common theme in the book. So, and yes, all the scripts in the book we want to put on a website so you can just grab all the scripts and start using them. That's the DTrace book, and it was a relief for me to do it because I suspected I might have had a few gaps in the DTrace Toolkit. I wasn't aware of it until I sat down and really thoroughly investigated everything. So it's a giant relief to get that done. But I mentioned it now in the presentation after looking at that diagram, because now we really do have a bunch of examples to look at every layer. Just as a quick peek at DTrace, but I think you guys have used DTrace, so I just had a slide for looking at syscall entry for processes called xorg, and we're aggregating on probefunc and the user stack backtrace. And just as an example, here's DTrace showing not just counting the system calls that this application is calling, but also showing us why the application is calling those system calls. So stack traces are really, really important. They show us the path. If you read through them, you may not understand them, but if you're interested in applications, such as this session is, then you may have access to the source code, so you can go and read the layers of the stack and find out what's going on. It's a very strange thing when I first did it with DTrace, but it works quite well, and that's the concept of frequency counting stack traces. When I first thought of frequency counting stack traces, I thought, and here, we mean using a stack trace, a stack backtrace, as a unique ID. I don't know if you've looked at much stack backtraces, but they don't look particularly unique. Why would I have more than one occurrence of these things? It turns out you do have a lot of more than one occurrence of these things. If I'm calling a system call in a loop, each time I call it, I have the same stack backtrace. If I'm profiling, instead of using the syscall measurement of the stack, and there's a hot code path, that stack backtrace may be frequent as well. So it turns out frequent stacks is something that does actually happen a lot. So finishing off just the introduction to DTrace, unified observability, normal software analysis tools often constrain view. Language specific, software layer specific, tied to a development framework or non-production use. And it's the same for system tools, like if I'm using IOStat, I just get what options it gives me, despite it being a great tool. VMstat, the same deal. Top, PRstat. DTrace can see all, so you can locate bugs no matter where they are, and you can locate latency no matter where they are. If you're a manager of a team of application engineers, this makes your job a little bit easier, because if you're telling people to go and troubleshoot a bug, you can say, use DTrace to find it. And they can't really say, oh, DTrace doesn't do it. DTrace can do it. DTrace can look at every single, all pieces of the function, all pieces of the software stack, sorry, all functions no matter where they live. That's particularly important, especially in terms of, so I've worked with application developers who, if you ask them about performance analysis, they say, we're really good at performance analysis, we know how to use our toolset really well, we understand what our code is doing, and they're not quite aware that they're looking at their layer of the software stack that they know really well. Maybe that layer is Java, or it's JavaScript, or it's PHP. Bugs happen everywhere. Performance problems happen everywhere. One memorable example I had of this was a customer who hit a Java problem. And they had all sorts of analysis of the Java layer, and they weren't able to really figure it out. And it turns out that the Java problem they were hitting was a bug in libc and how it was doing mutex locks. Now, if a customer actually told me that, I would think they're making it up. And it's like, libc is a fairly standard library. Mutex, the way mutex locks work, that's fairly standard. There's not going to be a bug there. But it turns out there was a bug there, and they were able to prove it with DTrace. And so when the DTrace output, when they were showing the DTrace output, that really got our attention. And we couldn't ignore it anymore because it was a real measured, quantified problem. And it was good that they were thinking outside the box. Java itself, if you do Java, is complicated enough as it is. And you have a rich tool set to do analysis of the JVM and how that's operating. But there is the rest of the system, and bugs can happen anyway. Connecting the dots. So showing system activity in application context, and correlating system resources to who and how they are used. Various features, just to mention briefly. So DTrace, its name comes from dynamic instrumentation, which I'll explain. But there's also static instrumentation. Has a unified interface, so you just learn one tool and it can examine everything. Arbitrary context kernel instrumentation, guess if you've used kernel debuggers, that may make more sense. So you can look at anything. And it has a lot of features for data integrity, giving you a high-level control language. Scalable is important. So one problem we're hitting with tools, you've got systems these days with hundreds of virtual CPUs, and if I'm tracing software on low CPUs, your tracing framework needs to scale as well. You don't just have the problem of your application code needs to scale across 100 CPUs, but your tracing framework needs to scale across 100 CPUs. Otherwise, the tracing framework will be the bottleneck. And that's something DTrace has taken very seriously. So that was what is DTrace quickly. Using DTrace. If you're still learning DTrace, one of the big problems, and it's one of the main tasks for any technology, is just learning how to talk the talk. In 1 hour, it's difficult for me to show you everything there is to DTrace for a giant topic like that, and to teach you how to do everything. One valuable thing I can do is teach you how to talk the talk and cover the terminology. Some of this you may know quite well, some of it you may not. But learning the terminology can sometimes be half the challenge. Once you understand the terminology, then you can go read the documentation and it all suddenly makes a lot more sense. So with DTrace, when we say consumers, a consumer is actually a user land program under user SBIN usually that consumes the DTrace facility from the kernel. We've got one program, user SBIN DTrace, that's what lets you do one-liners and scripting. Probes. Probes are a point of instrumentation and data generation, and user-defined actions can be executed when probes fire, and probes are what DTrace examines. Providers are libraries of probes, and terminology matters here. We have static providers versus dynamic providers. So I've got a couple of examples here, and by example, it may be the easiest way to explain the difference. So for dynamic providers, say for FBT. FBT is function boundary tracing. It's called function boundary tracing because we're looking at the entry and exit of kernel functions. And on the subsequent slides, we explain the syntax. But here we're looking at a kernel function arc read, which is from ZFS, and we're looking at the entry point. For an application, here's a different provider. It's called PID. It's associated with a particular process ID, and we're looking at libc's, strlen, and we're looking at the entry to strlen. These are dynamic because libc could have any number of functions. I can also point it at my application, which may be written in C or whatever. It could have thousands of functions, tens of thousands, hundreds of thousands. So these are generated on the fly. And it's the same for the kernel. The kernel consists of tens of thousands of functions. These are dynamically generated, and they change from one release to the next. You update your application, you recompile, you may have changed the name of some functions or the arguments or the return values. So dynamically generated. Statically generated providers are typically hard-coded into the source. These don't change, they give you a stable interface. So we've got things like IO start for disk IO, proc exec success for when you start a new process. The Perl provider sub-entry for when you start a subroutine in Perl. PHP error for when PHP tosses an error. Interesting probe gives you the details. So these names are stable or static, and you can write scripts based on static providers that will continue to work without adjustments. Dynamic providers are very different. If I write a script, if I have my application version 1.6 and I write a DTrace script that analyzes it, I may need to keep maintaining that script as function names change and arguments change. It's just the nature of it, and that's why learning the terminology can be useful, because it's just a reminder about the nature of each of these. One's static and one's dynamic. And DTrace gets its name from dynamic, but that's not to say that static tracing isn't cool as well. It's very cool. Dynamic was something that DTrace did that was particularly new. A deprogram structure, just to explain that, it consists of a probe, or multiple probe definitions. In forward slashes, we have an optional predicate. Predicates are conditional, similar to an if-then else, but that decides whether to execute the action or the actions, which are in parentheses. This is called the clause. You have a series of actions when those probes fire. Getting to examples as quick as possible. So syscall read entry, if I'm Java, what this one does is it uses a special DTrace data type which begins with an @ sign called an aggregation, and we're frequency counting the process ID and the path name for read. This is kind of fancy, but sometimes it can be more illustrative to dive into the deeper end. Syscall read entry is the probe name. The first argument for a system call read is the file descriptor, and DTrace has this facility for us to turn the file descriptor integer into the path name. Because if we're doing analysis, we would prefer to see the path name. And then we've got reads. We're also frequency counting the process ID. This is, you can save this to a file and run it. So it has the interpreter line, hashbang user-spin dtrace -s. Or you can run it at the command line, dtrace -n for a probe definition, and then the entire thing is in single forward quotes to stop the shell from coming along and messing with it. Same thing, run at the command line. Since dtrace is very powerful, I do a lot of analysis from one-liners, and that's actually an important part of the book. I've done much more one-liners now than I did in the DTrace Toolkit. So there's 270 of them now. Especially with the introduction of higher level providers like the Perl provider and the PHP provider and MySQL. They allow you to write more powerful programs shorter. You can get away with one-liners. Sometimes they don't need to be scripts, which is a good thing. More terminology. And I see my PDF generation has messed this up a little bit. So we've got the 4-tuple name for a probe, provider module function name. The provider is the DTrace provider that manages the probe, which is the library of probes. Module is the kernel module or user library location, user segment, address space segment. We've got the function, and the name is the meaningful probe name. Something important about this is that it's the first and last members that matter. It's the provider name and the meaningful probe name that matter. The middle two, the module and function, are more there for observability. More there so that you know where DTrace instrumented something. So let's look at an example. And I'll do this on Mac OS X. So here I'm logged in as root so I can run DTrace. So I'll use DTrace -l to list probes, and I'll use a probe definition called IO start. And that tells me, ID is not that interesting, it's just a DTrace ID, I've never used them. Provider is the name of the provider I'm looking at, so this is the IO provider. IO is for backend IO, which is typically disks, but on Solaris it also includes NFS client backend IO. Doesn't do that yet on Mac OS X or FreeBSD, but potentially could. And then it's the last member that's important, which is start. That consists of the probe name, IO start. These two middle fields, Mac kernel and buff strategy, are more there for observational purposes to let me know where this is actually instrumenting. It's instrumenting the kernel in a function called buff strategy, which is almost the same as the Solaris function name, so similar roots in Unix. If I look at another provider, let's say proc, so it turns out the exec success, so in Unix when you create a process, you do a fork and then you exec the target. So on Mac OS X, there's actually two locations that it will, it instruments to satisfy this probe. So a function called POSIX spawn and a function called Mac exec VE. especially beginning with 2 underscores should ring an alarm bell. This is something you shouldn't be messing with. And it further illustrates the problem. So this is just observational. I know where that thing is, but it's actually proc exec success is the name of that program. In fact, let me just detrace this so you see something live. So I've enabled proc exec success. It says match 2 probes. We know why because we just saw it. Trace is a very simple DTrace built-in. It's like echo if you're a shell programmer, or print. Exec name is a DTrace built-in variable that is the process name being executed. If in another window I type in things like ls and then I can see what's that one? It was the underbar Mac exec the unified. In the action clause, I've specified print this stuff. DTrace has been kind and printed all the other stuff to help me out. If I don't want that, I use -q for quiet mode and it suppresses it. If I do man ls, here's the man page for ls, and I can see all the stuff that runs. So it ran 4 shells, then more, then groff, then grotty, then another shell, then gzip, then another shell, then gzip was this running as part of this? Yeah.
Yeah,
okay.
man page is usually zipped.
Ah, okay. Man page is usually zipped. I know I've done this demonstration before, but I'm kind of surprised each time. Maybe I've just done it before in Solaris. Alright, so it's actually running gzip to uncompress the man pages. Interesting. Some application problems are as simple as this. Just getting a high-level view of what's going on. When I used to do performance consulting, there were at least a couple that spring to mind where the application was performing badly because it was spawning a lot of processes to do its work. It was calling hundreds of processes per second. How do you normally identify that? I think one of the administrators was studious and noticed last pit in the output of top, which I don't see. Anyhow, it's not that easy. DTrace makes it easy. I can just as a one-liner and say, find out what processes are being fired on my machine. In fact, let's turn off my Wi-Fi. Airport D just fired. Let's turn, font worker and NMD lookup and what amount? Go back on. So, various macOS XE things are happening on my laptop and it's very trivial for me to figure out what they are.